3.2 Lesson 1, Difference, Quotients, and one definition of derivative. The objectives for today's lesson are 1. You will know the definition of the derivative of a function f at a point, and 2. You will use the definition of derivative of a function f at a point to find the derivative of a function at a point. So vocabulary for today: difference, quotient, we will see what that is, slope, average rate of change, slope of secant line, limit, instantaneous rate of change, derivative, slope of tangent line. And we'll see how these concepts relate. Let's consider an object moving along the x-axis. So here we have the x-axis. The distance of the object from the origin at time t seconds is given by f of t is equal to t squared. The object is at the origin at t is equal to 0 seconds. T values are negative as the object approaches the origin and positive as the object moves away from the origin. So for example, let's consider the function f of t is equal to t squared. So we can look at a table of values for t and f of t. So as the problem states, the object is at the origin at t is equal to 0 seconds. So when t is equal to 0, you have 0 squared, which is 0, and the object would be at the origin at t is equal to 0 seconds. The object is at the origin at t is equal to 0 seconds. T values are negative as the object approaches the origin. So you can have t values that are negative, for example, -3, -2, -1. And what's going on when t is equal to -3? -3 squared would be 9. The object would be here at t is equal to -3. -2 squared would be 4. The object would be here at t is equal to -2. -1 squared would be 1, and the object would be here at t is equal to -1. And you can see that the object is approaching the origin for these values of time. So t is equal to -3, -2, -1. The object approaches the origin. So t values are negative as the object approaches the origin, and positive as the object moves away from the origin. So when t is equal to 1, we have 1 squared. When t is equal to 2, we have 2 squared is 4. When t is equal to 3, we have 3 squared is 9. So when the t values are positive, then the object begins to move away from the origin. So when t is equal to 1, we would be here. When t is equal to 2, we would be here. And when t is equal to 3, we would be here. So the object approaches the origin as the t values go from -3 to -2 to -1. The object is at the origin at t is equal to 0, and the object moves away from the origin for positive values of time. So we have this problem about an object moving along the x-axis. Its distance from the origin at time t seconds is given by f of t is equal to t squared. The object is at the origin at t is equal to 0 seconds. T values are negative as the object approaches the origin and positive as the object moves away from the origin. So now let's take a look at the first question that we want to answer. Find the average rate of change of the object's distance from the origin on the time interval from t is equal to 1 to t is equal to 3 seconds. As the problem states, f of t is equal to t squared gives the object's distance from the origin. So we can find the distance the object is from the origin at t is equal to 3, and subtract from that the distance the object is from the origin at t is equal to 1. So that would be the change in distance, which would be measured in units, and we can divide that by the change in time, which would be measured in seconds. So this average rate of change would be f of 3, which is 3 squared, which is 9, minus f of 1. 1 squared is 1, divided by 3 minus 1. 9 minus 1 is 8, 3 minus 1 is 2, so that would be 4 units per second. So that would be an average rate of change. Now suppose I change the problem so that I have part B here, and find the average rate of change of the object's distance from the origin on the time interval from t is equal to 1 to maybe t is equal to 2 seconds. So f of t is equal to t squared gives the object's distance from the origin. And if I wanted to find the average rate of change of the object's distance from the origin on this time interval, I would find the change in distance, which would be now f of 2 minus f of 1, divide that by the change in time, 2 minus 1. So f of 2 would be 2 squared, which is 4. And I would have the change in time, which would be 2 minus 1. So the change in distance from the origin would be 3 units, and the change in time would be 1 second. So the average rate of change of the object's distance from the origin on the time interval from t is equal to 1 to t is equal to 2 seconds would be 3 units per second. Now we look at part C, approximate the instantaneous rate of change of the object's distance from the origin at t is equal to 1 second. F of t is equal to t squared gives the object's distance from the origin. So we can go back to what we did in parts A and B. In parts A and B, we found average rates of change of the object's distance from the origin on time intervals from t is equal to 1 to 3 seconds, and then from t is equal to 1 to 2 seconds. So in part A, we did the change in distance from the origin divided by the change in time, and that had units of units per second. In part B, we did the change in distance from the origin divided by the change in time, and that also had units of units per second. In part C, we can generalize what we saw in parts A and B. So instead of from t is equal to 1 to 3 seconds, or from t is equal to 1 to 2 seconds, we can go from t is equal to 1 to t seconds. And t could be 3, as we saw in part A, or t could be 2, as we saw in part B. But now we have the ability to make t very close to 1. And if we have a t value that is close to 1, we will have a very short interval of time, and our average rate of change of the object's distance from the origin on a very short interval of time around t is equal to 1 can be used to approximate the instantaneous rate of change of the object's distance from the origin at t is equal to 1. So a good approximation for the instantaneous rate of change of the object's distance from the origin at t is equal to 1 second, for example, could be obtained by choosing t to be very close to 1, like 1.01 seconds, and you'd have this. And the units would be measured in units per second. It is a rate of change of position with respect to time, or velocity. So this would be an approximation for the instantaneous rate of change. But we know that the closer t gets to 1, the better the approximation will be. And take a look at what we're about to do now. We're going to say that we will look at this difference quotient, and we will take the limit of this difference quotient as t approaches 1. In other words, as t gets closer and closer to 1, which means we will be considering a time interval that is very short, near t is equal to 1. And when we take the limit of this difference quotient, this limit will tell us the exact instantaneous rate of change of the object's distance from the origin at t is equal to 1. And what is the rate of change of the object's distance from the origin at t is equal to 1 second, it is the object's velocity, because velocity is a measure of the rate of change of distance with respect to time. So we're talking about the object's velocity at t is equal to 1 second. And this limit is what we will say is the exact instantaneous rate of change of the object's distance from the origin at t is equal to 1 second, which we also call the object's velocity at t is equal to 1 second. And we also call this the derivative of the function f with respect to t at t is equal to 1 second. So this is called f prime of 1. This is the derivative of the function f at t is equal to 1 second, given by the limit of this difference quotient, and it tells us the instantaneous rate of change of the object's distance from the origin at t is equal to 1 second, which is the instantaneous velocity. So we just saw the definition of the derivative of a function f at a point. It is defined as the limit of a difference quotient. The only difference between what you see here and what I wrote on my previous screen is what I wrote f of t minus f of 1 over t minus 1. And I took the limit of that as t approached 1, and I wrote that as f prime of 1. So the differences are, my function was a function of t, but your function could be a function of a different variable. It doesn't really matter. Your function could be a function of t, or a function of x, or a function of theta. It really makes no difference. I had 1 and f of 1 because I was trying to get the instantaneous velocity of the object at t is equal to 1 second. I could have done it for a different value of t, so more generally you have c and f of c. And you have this difference quotient. That's one of our vocabulary terms, difference quotient. And you take the limit of that difference quotient as x gets closer to c, as x gets closer to c. So in our example, the times we're getting closer to t is equal to 1. So you had this difference quotient telling us an average rate of change or average velocity of the object. And then we took the limit of that difference quotient as t approached 1, and that gave us the instantaneous velocity of the object at t is equal to 1, which we also call the derivative of the function f. Also, for you to understand is that this difference quotient is really taking a change in output values divided by a change in input values for the function f. So it's actually giving you the slope of a secant line passing through the 2 points c, f of c, and x, f of x. So you have a change in y divided by a change in x, giving you the slope of a secant line passing through these 2 points. And that is equivalent to the average rate of change of the object's position with respect to time, or average velocity of the object. And when you took the limit of this as t approached 1 in our example, or more generally as x approaches c, this will give you the instantaneous rate of change, which is called the derivative, and it will give us the slope of the tangent line to the graph of f at t is equal to c, or in our example at t is equal to 1. Our next objective is objective 2. You will use the definition of derivative of a function f at a point to find the derivative of a function at a point. So we were working with the function f of t is equal to t squared. You can change the variable for time from t to x. It really doesn't matter. So I'll go ahead and do that, and I'll write f of x is equal to x squared. We want to find f prime of 1, which would be the derivative of the function f at time is equal to 1, which would tell us the instantaneous rate of change of the object's distance from the origin at time is equal to 1, which would be also called the instantaneous velocity of the object at time is equal to 1. And how would we find the derivative? By using this definition. So we're going to write f prime of 1 is equal to the limit as x approaches 1 of f of x minus f of 1 divided by x minus 1. So when I say f prime of 1, my c value is 1, and that is why I have x approaching 1, and I have f of 1, and I have 1 here in the denominator. So now we'll go ahead and find this derivative. So we have the limit as x approaches 1. What is f of x? F of x is x squared. So I'm just going to write x squared here. What is f of 1? Evaluate the function at x is equal to 1. You get 1 squared, which is 1. Divide that by x minus 1. And how would we evaluate this limit? You will factor the numerator. You have a difference of 2 squares. So the numerator will factor as x plus 1 times x minus 1, because that's the factoring pattern for difference of 2 squares. And then you're able to cancel the common factor of x minus 1, and that would leave you with the limit as x approaches 1 of x plus 1. And because the polynomial function y is equal to x plus 1 is a continuous function for all real numbers, this limit will be equal to the function evaluated at x is equal to 1. So you can find this limit by what we call direct substitution, and this limit would be 1 plus 1, which is equal to 2. And what is 2? It is, by definition, the derivative of the function at x is equal to 1. And in the context of our word problem, it would tell us the instantaneous velocity of the object at time is equal to 1. And that would be in having units of units per second. So this is a difference quotient, and we want to look at the graphical interpretation of difference quotients and derivatives. In our problem with the object moving along the x-axis, our function giving us the distance the object is from the origin at time t was f of t is equal to t squared, or we can write f of x is equal to x squared, where x will now represent the time. And here's the graph of that function. So how do we graphically interpret this difference quotient? If you look at the difference quotient, we have a change in y divided by a change in x. So it is to be interpreted as the slope of a secant line through 2 points. One point will be the point 1 f of 1 on the graph of f, and the other point will be, it can be something that you choose depending on what you choose x to be. So for example, if you choose x to be 3, then we're looking at a second point on the graph of f at x is equal to 3, which would be right here, and you would have the point 3 f of 3. And this difference quotient would give us the slope of this secant line through these 2 points. And that is what you see here. We have 3f of 3, 3 squared is 9. And we have 1f of 1, 1 squared is 1. And here we have the secant line passing through these 2 points, which is the slope of that secant line is the value of this difference quotient. And it tells us the average rate of change of the object's distance from the origin on the time interval from t is equal to 1 to t is equal to 3 seconds. So the graphical interpretation of a difference quotient is that it tells us the slope of a secant line through 2 points. The interpretation of the difference quotient in the context of our problem is that it gives us an average rate of change of the object's distance from the origin on a time interval from t is equal to 1, in this case from 1 to 3 seconds. So if we generalize, we could have f of c and then f of x, and the difference between f of x and f of c divided by the difference between x and c. And this is a difference quotient, and we can take the limit of this difference quotient as x gets closer to c. And this is the definition of the derivative of the function f at x is equal to c. And we notate that f prime of c. So what's going on? As x is approaching c, this is what's happening. So we have 2 points. One point is c f of c, and the other point is x f of x. And in this limit, which is the definition of the derivative, x is approaching c, which means this second point is getting closer to the first point. And when we take the limit of the difference quotient as x approaches c, we get what we call the derivative of the function f at x is equal to c. And it tells us the instantaneous rate of change of f with respect to x at x is equal to c. In the context of our word problem, it would tell us the instantaneous rate of change of the object's distance from the origin with respect to time at time is equal to 1 for our word problem, which is called the instantaneous velocity. What about graphically? What is the graphical interpretation of this derivative? This is called the derivative of the function f at c. What is the graphical interpretation of this derivative? The difference quotient gives us an average rate of change, or the slope of a secant line. But what happens as the second point moves closer to the first point to give us this limit, which is the derivative? So consider this secant line passing through c f of c and x f of x. Of course, we're using c is equal to 1 in our example. And here we have an x value, that is x is equal to 2. We had x is equal to 3 in our previous graph, but now we have x is equal to 2 here. And this is still the slope of a secant line. But what happens as this second point moves closer and closer to the first point? That's what we're talking about when we take the limit of this difference quotient as x approaches c. It gives us the derivative, and the derivative, the graphical interpretation of the derivative is that it will give us the slope of the tangent line to the graph of f at x is equal to c. So this derivative, the graphical interpretation of it is that it gives us the slope of the tangent line to the graph of f at x is equal to c. So let's review what we've done so far. We have looked at the definition of the derivative of a function f at a point. In that definition, we saw a difference quotient, which gives us the slope of a secant line. In the context of a word problem, it would give an average rate of change. And when we took the limit of that average rate of change, when we took the limit of that difference quotient, it gave us the instantaneous rate of change at a particular value of time, which we also call the derivative. And graphically, that derivative gives us the slope of a tangent line. We've also seen objective 2. We use the definition of derivative of a function f at a point to find the derivative of a function at a point. We've already seen an example of that. Let's look at another example for objective 2, where we use the definition of derivative of a function f at a point to find the derivative of a function at a point. So now we take a look at number 5. Use the definition of derivative, which is right here, to calculate f prime of c exactly. So our function is f of x is equal to x squared plus 5x plus 1, and the c value is negative 2. So what we want is we want to find f prime of negative 2, and that would be defined by this limit of this difference quotient. So we would take the limit as x approaches negative 2 of the difference quotient f of x minus f of negative 2 divided by x minus negative 2. Again, what is this difference quotient? It is a change in y divided by a change in x. So it's giving you the slope of a secant line passing through 2 points. The 2 points are negative 2, f of negative 2, and the second point would be x, f of x. And when we take the limit of this difference quotient as x approaches 2, we're making the second point move closer to the first point. And this limit of this difference quotient will give us what we call the derivative of the function at x is equal to negative 2, which is the instantaneous rate of change of f with respect to x at x is equal to negative 2. And the graphical interpretation of this derivative is that it will give us the slope of the tangent line to the graph of f at x is equal to negative 2. So let's find the derivative of f at x is equal to negative 2 by using this definition, and then we will use the derivative, which will give us the slope of the tangent line to the graph of f at x is equal to negative 2 to sketch the graph of the tangent line to the graph of f at x is equal to negative 2. So we begin with the definition of derivative at a point. So we have f prime of negative 2 is the limit as x approaches negative 2 of f of x, which is right here, minus f of c minus f of negative 2 divided by x minus c, divided by x minus negative 2. So now we will just evaluate this limit. So what is f of negative 2? So you just evaluate the function f at x is equal to negative 2, and that would give you 4 plus negative 10 plus 1, which would be negative 5. So f of negative 2 is negative 5. So we replace f of negative 2 with negative 5, and here we have minus negative 5. Minus negative 5 is the same as adding 5. So we write plus 5, and in the denominator I have minus negative 2, which is the same as adding 2, so I have plus 2. And I can combine these two constants in the numerator. 1 plus 5 is 6. So I will have this. And now to take this limit, I can factor the numerator. To take this limit, I can factor the numerator. The numerator will factor as x plus 2 times x plus 3. When you multiply x plus 2 by x plus 3, you will get x squared plus 5x plus 6. And now that you've done that, you can cancel the common factor of x plus 2, leaving you with the limit as x approaches negative 2 of x plus 3. And since x plus 3 is a continuous function for all x, you can find this limit by doing direct substitution, and that would be equal to negative 2 plus 3, which is equal to 1. And what is that equal to? Of course, that is equal to the derivative of the function f at x is equal to negative 2. That is, in fact, equal to 1. And what does this tell us? It tells us the slope of the tangent line to the graph of f at x is equal to negative 2. So here we have the graph of the function f of x. And here we have the graph of the tangent line to the graph of f at x is equal to negative 2. And the slope of this tangent line was given by the derivative of the function f evaluated at negative 2, which we found to be 1. So today we looked at these two objectives. We now know the definition of the derivative of a function f at a point, and we were able to use the definition of derivative of a function f at a point to find the derivative of a function at a point. In this definition, we take the limit of a difference quotient, and that limit of a difference quotient gives us the derivative, which gives us the slope of the tangent line to the graph of f at x is equal to c, and that derivative also gives us an instantaneous rate of change of f with respect to x at x is equal to c.